So whenever we are learning about something new, it's very important that we understand the notation in whichever kind of literature we are studying. And let's talk a little bit about the notation in chapter 1, because before we enter week 2, there are some symbols that we need to make sure that we understand. And among these symbols are, well, here are a couple of them. So what does F stand for in chapter 1? What does FJ stand for in chapter 1? What does YJ stand for? What does Y of TJ stand for? And what do we mean when we say something like, for example, TJ plus 1 or TJ minus 1? And what do we mean when we say something like K or M or T? So let's just clear this up once and for all, because in many of the exercises you will do this week, you need to understand, what does this mean? 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 And so on and so on. Now, if we start off with F, F is used in two ways in chapter 1, which actually confuses more than is well, it's quite confusing. But first of all, in table 1.1 in Holmes, F just stands for a function. Any function that is differentiable. And in the rest of chapter 1, F is used to represent the differential equation, the expression that defines our differential equation. So F is actually the representation of y prime of t, where we recall that already quite early in the chapter they use this kind of notation that says y prime of t equals f of t comma y, and then they will write something like, well, that might be t times cosine of t times y of t, or something like that. So this is what F is used to denote primarily in chapter 1. It is a representation of y prime of t. Now, what is Fj then? Well, Fj is equal to F evaluated in Tj, comma, Yj. Now, note that this is not the same as F evaluated in Tj, comma, Y of Tj, and we will arrive at why this is the case here in the next step, because it's also very important that we understand the difference between Yj and Y of Tj. Now, Y of Tj is the exact solution to the differential equation y prime of t equals f of t comma y, but just evaluated in the point tj, whereas yj is the approximate solution of our differential equation evaluated in Tj. And this means that these two numbers, yj and ytj, well, they are different. And that's also the reason why I said that f of tj comma yj and f of tj comma y of tj are different. And when we write fj here, we use it in the sense that it is the approximation of y prime based on tj and the approximation of yj, and the approximation of y in tj, so yj here. Now, just so that we are all on the same page, let me once again draw the grid that we use in chapter 1. So in chapter 1, we study the derivative y prime of a function y on a closed interval 0 to t, where we construct a finite difference scheme over a certain grid that has m time points. So we call these time points t0, t1, t2, etc., etc. And the difference between each of the time points is the same. And we say that this is k. Or sometimes we also call it h. Kind of depends on where you stand in the book. Sometimes it's h, sometimes it's k. So k is the step size. And m is the total number of time points after 0. And also, this leads us on to what tj plus 1 is. So if I have the value of tj, then tj plus 1 is equal to tj plus the step size, k. And this is something that we will have to use in a lot of the exercises in week 2, because we will sometimes have to evaluate y of tj plus 1 by doing a Taylor approximation expanded around tj. So tj plus k is the same as tj plus 1 in the index here. And in the same way, I have that if I take the time point tj and I go k time units backwards, so tj not plus but minus k, then I have tj minus 1. Okay, and this t down here was the length of our time interval. So now we should have cleared most of that up, and once again just repeatedly explain to yourself what fj, yj, and yt of j stands for, because these are quite important concepts. And just so that we are completely sure of what is going on, I would also like to remind you guys that often we have some kind of finite difference expression that, for example, if we consider the forward Euler method in the book, let me just find that in the book. Then they have yj plus 1 is equal to yj plus k times f of tj comma yj. where this, of course, is what they call fj. Then how does this thing relate to a corresponding expression where I have the exact terms? Well, the exact terms are y of tj plus 1 equals to y of tj plus k multiplied by f of tj comma y of tj. And then here I have on this side a truncation term minus k times tau j. So normally if I have the finite difference scheme, then I have a corresponding exact expression where I just substitute the approximations with the exact solutions, and then I also include the truncation term. And this is something that you will be working with in exercise 2.1, and to understand more about that, please watch the next video.